Dear students, very good morning to all of you. My name is Shukanta Dev. I will be teaching Mathematical Physics 2. This is my first lecture in this class. I will start this lecture with Fourier series. In this lecture, we will learn about periodic functions, orthogonality of sine and cosine functions, piecewise continuous function, and Fourier series. Periodic function. A function f of t is said to be a periodic function for all t if there exists a positive number capital T such that f of t plus capital T is equal to f of t. The number capital T is called the period of the function f of t. For example, sin t and cos t are periodic functions with period 2 pi. A periodic function f of t repeats after a regular interval of time capital T called the period of the function where t is greater than 0. Therefore, for a periodic function, we have f of t plus small n into capital T is equal to f of t, where n is any non-zero integer. Therefore, we can always write f of t is equal to f of t plus minus capital T is equal to f of t plus minus twice t, and so on, for a periodic function. That is, the value of the function spaced at any integer multiple of capital T must be the same both in the negative and positive time axis. The above definition of periodic function can also be extended to space as well as angular domain. This figure shows the graph of a periodic function with period capital T. We can see that this pattern of the function is repeating almost in an identical fashion towards the right as well as towards the left. That's why this function has a period equal to capital T. Now this figure shows a graph of a square wave function. We can see the same pattern is also repeating in an identical fashion towards the right as well as towards the left. Therefore, this function has a period equal to 4. Now, here this figure shows the graph of a periodic function with a period equal to 4. We can see that this is a complete piece of the wave, and this is repeated exactly in an identical fashion towards the right as well as towards the left. So, therefore, this function has a period equal to 4. Orthogonality condition of sine and cosines. Let f of t be a periodic function with period capital T and angular frequency omega, when omega is equal to 2 pi by capital T. If small n and small m are positive integers, then 0 to capital T sine of n omega t dt is equal to 0 to capital T cos of n omega t dt is equal to 0. Then also we have 0 to capital T sine of n omega t sine of m omega t dt is equal to capital T by 2 into delta nm, where delta nm is called the Kronecker delta function, defined as delta nm is equal to 1 if n is equal to m, else delta nm is equal to 0 if n is not equal to m. Again we have 0 to capital T cos of n omega t cos of m omega t dt is equal to capital T by 2 into delta nm. And lastly 0 to capital T sine of n omega t cos of m omega t dt is equal to 0 for all n and m values. Now these formulas imply that the functions sine of n omega t and cos of n omega t for n is equal to 1, 2 and so on constitute a mutually orthogonal set of functions in the interval 0 to capital T. Orthogonal functions. Two real valued functions ut and vt are said to be orthogonal in the interval 0 to capital T if 0 to capital T ut and vt dt is equal to 0. Where ut and vt, this shows that u is a function of t and v is a function of t, which is time. Now piecewise continuous function. Now this figure shows the plot of a piecewise continuous function in interval ab. Now within this interval, the function has been divided into 3 subintervals. Now each of the subinterval is basically continuous, but the function as a whole is not continuous, and there are points. At some points, the function experience discontinuities. Like here in this point, the function is a discontinuity. Again, the function is discontinuous at this point. Again, here the function is discontinuous. Now, at the point of discontinuity, so what we can do is that we can define a jump by using the the limit of the function at this point and the limit of the function at this point. Now this f of c plus is basically called the right hand limit of the function at c, and f of c minus is called the left hand limit of the function at c. Now the jump is defined as the difference between these two values. So, and the limit, right hand limit f of c plus can be written as limit t tends to c plus f of t, and this is the usual definition of limit of a function. Then we can write down this as limit h tends to 0 f of c plus h, and f of c minus is equal to limit t tends to c minus f of t is equal to limit h tends to 0 f of c minus h. Now this figure shows a piecewise continuous function f of t, which is a period equal to capital T. We can see that at this points, at the point capital T, 2t and 3t, the function is a discontinuity. Okay, but otherwise the function is a regular pattern, up to a length capital T, and after that at the point T the function has a discontinuity, and the same pattern repeats. Okay, that's why the function is a piecewise continuous periodic function with a period capital T. Fourier's theorem. According to Fourier's theorem, any single valued continuous or piecewise continuous periodic function can be written as the sum of an infinite number of simple harmonic motions having angular frequencies which are integral multiples of the angular frequency of the given function. Single valued means that means the value of the function corresponding to a particular value of t is distinct. Okay, so now so if we assume that f of t is a single valued continuous or piecewise continuous periodic function with period capital T and angular frequency omega, which is defined as omega is equal to 2 pi by capital T, then according to Fourier's theorem, f of t is equal to a naught plus a1 sine of omega t plus phi 1 plus a2 sine of twice omega t plus phi 2 plus a3 sine of 3 omega t plus phi 3 up to infinity. Now these are all simple harmonic motions. This is a simple harmonic motion with an angular frequency omega. This is a simple harmonic motion with an angular frequency twice omega. This is a simple harmonic motion with angular frequency thrice omega. And apart from all these simple harmonic motions, then we also have a constant term. Okay, this is basically known as the B.Sc term of the Fourier's theorem. Now we can write down this f of t is equal to a naught plus summation over n is equal to 1 to infinity and an sine of n omega t plus phi n. And this is the mathematical statement of the Fourier's theorem. Now we can expand this because we can see that this is a form of sine of a plus b. So we will expand this here, and expanding the above function, we can write down f of t is equal to a naught plus summation over n is equal to 1 to infinity an sine of n omega t cos of phi n plus cos of n omega t sine of phi n. And then from here we get f of t is equal to a naught plus summation over n is equal to 1 to infinity. Then we can separate this terms which do not contain t. So these are an cos of phi n, and we write them together, and we have this an cos of phi n sine of n omega t plus summation over n is equal to 1 to infinity an sine of phi n cos of n omega t. Now let us write down this as capital An, okay, and an sine of phi n as capital Bn. So therefore the final expression of f of t becomes f of t is equal to a naught, it's capital A naught, where the capital A naught is nothing but small a naught, and so plus n is equal to 1 to infinity an sine of n omega t plus n is equal to 1 to infinity bn cos of n omega t. And this is known as the Fourier series expansion of a periodic function f of t having period capital T and angular frequency omega. Now in the above equation we have substituted capital A naught is equal to small a naught and capital An is equal to small an cos of phi n, and capital Bn is equal to small an into sine of phi n. And this a naught, an and bn are called the Fourier coefficients. So therefore we have the Fourier series of a single valued continuous or piecewise continuous periodic function f of t having t lying in the interval 0 to capital T, or t lying in the interval minus capital T by 2 to capital T by 2, where capital T is the period, is given by f of t is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n omega t plus summation over n is equal to 1 to infinity b n cos of n omega t. These coefficients a naught, a n and b n are called the Fourier coefficients and are given by these expressions. So capital A naught is equal to 1 by t into 0 to capital T f of t dt. So this is nothing but it's a mean value of the function over the interval 0 to capital T. So we can write down this also equal to 1 by capital T, and this interval 0 to t can be written as minus t by 2 to plus t by 2. So therefore a naught becomes equal to 1 by t 0 to capital T f t dt is equal to 1 by t minus t by 2 to plus t by 2 into f of t dt. Similarly, a n is equal to 2 by t into 0 to t integral of f t sin of n omega t dt is equal to 2 by t, and integral from minus capital T by 2 to plus t by 2 f of t sin of n omega t dt. And lastly, we have this the value of the coefficient b n, and which can be obtained as capital B n is equal to 2 by capital T and 0 to t f t cos of n omega t dt, and this is equal to 2 by t, and we can just write down this interval 0 to capital T as minus t by 2 to plus t by 2, and rest of the the expressions remain the same. So here n denotes the number of terms of the Fourier series, and omega is equal to 2 pi by t is the angular frequency of the periodic function f of t. It should be noted that f of t plus capital T is equal to f of t, where f of t is a periodic function having period capital T. So here shows the graphs of partial sums of the Fourier series of the square wave functions with a number of terms. Here I should write down small n, so because I have used a small n, so number of terms n is equal to 3. So if I put n is equal to 3 in my expressions, then this function can be approximated as follows. Similarly, with 6 terms, this function can be approximated, shown in the blue color, and with 12 terms, this function can be approximated like this, and with number of terms equal to 24, the function can be approximated like this. So we can see that the given function, square wave function, can be approximated by a summation of a large number of terms. Similarly, the Fourier series of a single valued continuous or piecewise continuous periodic function f of x having x lying between minus L to plus L, where twice L is the period, is given by f of x is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n pi x by L plus summation over n is equal to 1 to infinity b n cos of n pi x by L, where a naught, a n and b n are called the Fourier coefficients, given by a naught is equal to 1 by twice L minus L to L, integral over minus L to L f of x dx. Again, this is nothing but it's a mean value of the function over the length minus L to L, or from 0 to twice L. And similarly, a n is equal to 1 by L minus L to L f of x sin of n pi x by L into dx, and b n is equal to 1 by L minus L to L f of x cos of n pi x by L into dx. Note that this this limit minus L to L can also be written as 0 to twice L. So we note down that f of x plus twice L is equal to f of x, because f of x is a periodic function having a period equal to twice L. Now we can actually get this expression simply from the time domain expression of Fourier series. Now how to get these expressions from the time domain Fourier series? So let us see how it is done. So in the frequency in the time domain we have t, but in the space domain we have x. Similarly, in the time domain we have the capital T as the period, and in the space domain twice L is the period, and therefore the interval 0 to capital T in the time domain can be written in the space domain as 0 to twice L, because twice L is the period in the space domain. or we can write down this 0 to t as minus t by 2 to plus t by 2. Similarly here we can write down this minus L to plus L. Now angular frequency in the time domain is equal to twice pi by capital T, but in the space domain capital T is equal to twice L, so we get omega is equal to pi by L. Therefore this quantity n omega t, this quantity n omega t, we have already seen that this expression in the time domain involves n omega t in both these two terms. So therefore we find this n omega t in the space domain as n. Now omega is pi by L, and in the space domain t is replaced with small x, so we have n omega t is equal to n pi x by L. So therefore we write down the expression for the Fourier series in the time domain, and replace or substitute the corresponding values of the time domain with the values as those of the space domain. So t is replaced with x, and this again n omega t is nothing but n pi x by L, and similarly here we replace n omega t by n pi x by L, and therefore the Fourier coefficients becomes in the time domain, we know that it is given by a naught is equal to 1 by capital T, so this integral 0 to capital T f of t dt. So now or we can write down the 0 to t as minus t by 2 to plus t by 2. So similarly in the in space domain we can write down this a naught as equal to, because in the space domain twice L is a period, so instead of t we write down twice L. So therefore we get a naught is equal to 1 by twice L, 0 to twice L, f of x dx is equal to 1 by twice L minus n2 plus L f of x dx. Similarly we can find an is equal to 1 by L, 0 to twice L, fx sin of n pi x by L into dx. It is also written as 1 by L minus L to L f of x sin of n pi x by L into dx. And lastly you can write down Bn as 1 by L into integral 0 to twice L f of x cos of n pi x by L into dx. And this, as we know that this interval can be written as minus L to plus L, and rest of the terms appear as it is in the expression. Also the Fourier series of a single valued continuous or piecewise continuous periodic function f theta, where theta is any angle whose values lie in the range 0 to 2 pi or minus pi to plus pi, and here 2 pi is the period. So f theta can be written in a Fourier series expansion as f theta is equal to a naught plus summation over n is equal to 1 to infinity a n sin of n theta plus n is equal to 1 to infinity bn cos of n theta, where a naught, a n and bn are called the Fourier coefficients given by a naught is equal to 1 by 2 pi 0 to 2 pi f theta d theta. This is again the decision or the average value of the function over the complete period. And this can also be written as 0 to 2 pi can be written as minus pi to pi, and therefore a naught is equal to 1 by 2 pi into minus integral minus pi to pi f theta d theta. Similarly we can find a n is equal to 1 by pi into 0 to 2 pi f theta sin n theta d theta, and this is also equal to 1 by pi minus pi to plus pi f theta sin n theta d theta. And lastly we get bn is equal to 1 by pi 0 to 2 pi f theta cos of n theta d theta, and this can be written as 1 by pi integral from minus pi to pi f theta cos of n theta d theta. So here we should note down that f of theta plus 2 pi is equal to f theta, because f theta is a periodic function having a period equal to 2 pi. Thank you. So if you want to have any queries, you can write to me in this email address. You can give me a call, or you can visit my website and submit your query. As well as you can submit your queries in WhatsApp and as well as Google Classroom. Thank you.